A sincere thanks is given to all of the sponsors and the individuals who contributed their time and effort into making this test a reality. A special thanks is given to Mr. Gerald Groswald and the Winter Park Board of Directors, who allowed this lift to be used in a testing situation to further lift knowledge and the understanding of what forces are involved in a lift catastrophe. The brake test was designed to show the dynamic effects on the lift and the capabilities of the braking systems in a rollback situation, where the speed of the lift was allowed to achieve a higher velocity than is normally experienced during a typical load test.
Yeah.
In the service brake full-speed rollback, the service brake would not stop the lift, and the bull wheel brake had to be applied to bring the lift back under control.
Yeah. Stop the lift.
Oh, would not.
Would not work.
The smoke billowing from the motor room vault was a result of the burning brake shoes on the service brake. In the bull wheel brake full-speed brake test, the bull wheel brake very adequately slowed and stopped the lift from approximately 550 feet per minute in reverse.
I'm rolling.
Although the brake shoes showed signs of overheating as evidenced by the smoke, the brake functioned quite adequately and brought the lift to a stop with a maximum deceleration rate of 1.53 feet per second squared. During this test, the haul rope derailed on the upgoing side at the upper terminal when a chair was lodged in the guidage. Although the cable was not retained by the cable catcher, the cable did break the derail switch, and it functioned as it was designed. For the next test, the low-speed shaft was disconnected from the gearbox and electric motor. This was done to see if there was a difference in acceleration if the gearbox and electric motor were not adding friction to the lift in a reverse situation. The control panel for this lift has two stop buttons. Inadvertently, the normal stop button was depressed instead of the one controlling the bull wheel brake. This resulted in an uncontrolled reverse rotation of the lift with fully loaded chairs on the heavy side. The lift stopped from chairs getting caught in the machinery and other external friction forces. After the lift rolled to a stop, the scenes were devastating. The guidework at the terminals had been bent, as if made out of rubber. Concrete blocks had been hurled up to 120 feet through the air, and shiv trains had been bent and some pulled off the crossarms. Chairs had been thrown everywhere, and chair stems had been broken in half and bent like pretzels. Clips had been dragged backwards through the haul rope, and one shiv wheel axle failed catastrophically. At the top, the scenes were very similar.
You know something like this is potential, so then you're saying, well, this is it. I'm going to watch it and soak in as much as I can.
After this event, it was wondered if the test could continue. But through the hard work of the Winter Park lift mechanics, the lift was ready to run the next morning. The oily rope test was designed to show what forces may come into play in the event there was a major oil leak that flooded the haul rope and the bull wheel. On this particular lift, the tensions were such that the lift was unable to drive the cable in an oily condition, but the lift would not roll back and or allow the rope to gain momentum in a reverse direction simply due to the oil on the haul rope. During this test, the rope reached a maximum temperature of 250 degrees Fahrenheit.
On the bull wheel, please.
Starting to smoke.
Okay. Right on the bull wheel. Watch it.
Want to save the liner?
Okay, stop it.
Save the liner.
Yep.
Save the liner.
Okay, stop it.
Start at the top. Start to move.
Top ready?
Okay.
The next test was designed to show the dynamic effects on the lift from a tree falling against the lift while the lift was moving. At the bottom of the lift, the results were dramatic due to two factors: the size of the tree that was available to fall on the line and the lower tensions encountered at the bottom of the lift. two trees that were felled on the lift towards the top had a much less dramatic impact. The impetus behind the entire test was the fire test. The lift motor room was a vault type with concrete walls and floor, and a wood frame roof and attendance building on top. This fire was started by lighting some oily rags that had been soaked in diesel fuel and placing them under a workbench in a remote corner of the motor room. The fire was visible to people at the outside of the lift within 27 seconds.
Yeah, we're getting 338, 344. 400. I'll keep it sighted in. 410. 424.
You right on the door? Or?
We're on Jim Fletcher's head.
Hey, how come it's stopped?
455. 450, 1 minute after.
It's stopped?
480.
E-brake right.
Oh, damn, we didn't hear.
That's the e-brake.
Let's see if we've got control power. Jim Fletcher.
I think we're trying to drive through the e-brake.
All right.
Yeah, because we lost.
Yeah, we still got control power.
Brake is down.
Power off. Turn off the power.
The other two.
1 minute and 8 seconds after the fire became visible, the lift stopped due to a loss of hydraulic pressure in the bull wheel brake. The fire reached a maximum temperature of 1800 degrees Fahrenheit 6 minutes and 15 seconds after the fire was evident, and the temperature remained above the 1500 degrees Fahrenheit mark at the rope from the 5 minutes and 30-second mark until after the 15-minute mark. The heat was measured using a radiometer that could measure the average heat in a 1.5-foot diameter circle from a distance of 100 feet. Because this test was conducted at a time when the fire danger in the surrounding forest was moderate to high, a professional firefighting team was stationed around the lift with enough firefighting equipment to control any fire that may have resulted.
$1,600, 1,700 degrees. Uh, 1,600 degrees Fahrenheit.
Come down now, huh?
Yeah, a little bit. Peaked at about 1800. Look at those two.
The resulting break in the cable was as expected, and although the lift had been unloaded prior to the fire test, the dynamic effects along the lower portion of the lift were dramatic.
Yeah, a little bit. Peaked at about 1800.
What was interesting is that above Tower 8, the cable did not derail from the sheave wheels. The tower pull test was conducted last, and two types of foundations were tested, a shallow block footing and a deep block footing. The deep block footing was installed by the original equipment manufacturer.
Bob? Jim, Warner was also noticing the pulling angle right now looks very, very close to 90 degrees. Wait, just 1 second. And the tower buckled approximately 3 feet off of the concrete, and the concrete opened up about a little over 3/16 of an inch.
You want to hold it right there where that mark is
Right to
edge
the...
of the concrete.
Yeah, but down in the... Can we pull that out, guys? Okay, yeah. That's interesting.
One like that size.
It's buckled. It's buckled. Airtight.
The lift was later modified and several towers were added so that the tension carriage movement could be minimized. In this modification, a shallow block footing design was used, thus allowing us two types of footings to test.
Okay, Jim, why don't you stop it there for just 1 second? Let's get the
Can you guys, do you think you could move this camera around to here and take a look at it right here?
Yep.
In the course of doing the tower pull test, there were several interesting discoveries. 1. The inside of all of the towers showed almost no corrosion. In the deep block footing perpendicular pull, the weld failed, allowing the tower to fall over. Although the weld failed, you could see that the tower tube itself was very close to yielding, as witnessed by the bending that the tower tube had undergone just prior to the catastrophic failure of the weld. In conclusion, thanks to all the individuals and sponsors who made this test possible.